Hello, can you hear me?
Yes.
Yes.
Oh, I'm really sorry about the technical challenges I'm having with my internet. I really don't understand what is happening. Okay, so let me just do this. I hope this time I'm going to go through it. Well-known attributes and optional attributes. So we've said with well-known, it must be identified and also supported by all BGP routers. When it comes to optional, do not need to be identified and supported by all BGP routers. So that's the difference between these two. Now, under well-known, we have what we call well-known mandatory. And we also have one well-known discretionary. Now, with mandatory attributes, they must be carried. They must be carried in a BGP, update message. So, for example, examples of well-known mandatory includes the origin. We're going to look at the origin, the AS path, and also the next hop. So these must be carried in all the BGP update messages. Then discretionary do not need to be carried in a BGP update message. However, can be selected as required. Examples, we have the local preference. We're going to look at the local preference, and also another one we call atomic aggregate, which we're also going to look at. Now, when it comes to optional attributes, we have what we call the optional transitive, and we also have the optional non-transitive. So what's the difference between these two? With optional transitive attributes, these ones cannot be identified by some BGP routers, but can be carried in BGP messages and advertised to neighbors. So it can be advertised to neighbors, it can be carried. So even though you don't understand that particular attribute, you can carry it. So we're going to see, for example, the aggregator attributes and the community, the community attribute. So those are examples of optional transitive. Now with optional non-transitive, transit simply means you can carry it, even though you don't understand it, you can carry it. And non-transitive is the opposite. So this one, a BGP router can ignore the messages carrying these attributes, and does not advertise these messages to the neighbors. Excuse me. So generally, with non-transitive, it does not advertise to the neighbors. Transitive, it can advertise to the neighbors. because it can carry it. Yes, I don't understand these attributes and what it means, but I can carry it and advertise it to the neighbors. Here, I simply ignore the message and do not advertise it to the neighbors. So examples include what we call the multi-exit discriminator, which we're also going to see in a short while. Okay, so let me hang on that. So the very first attribute we're looking at is the origin attribute. The origin attribute. Origin. The origin attribute is a well-known mandatory, meaning all the routers must carry it. Now, the origin attribute defines the origin of a route. The origin of a route is how it becomes a BGP route. So how did it become a BGP route? In this example, we have the network segment 200.0.0.0/24 on RTD, which is on AS 200. Now on AS 100, we have the router RTA. Now RTA can learn about this network segment 200 from two sources, RTB and also RTC, using EBGP. Now it learns that particular network using the network command from RTB and using the import command from RTC. Now, as you're going to see, the origin of an attribute can determine which route is actually the best route. Now you can see here in RTA, if we do display BGP routing table, we have an entry. We have two entries that can take us to this network. So we can either go through RTB, which is 2.2 there, or we can go through RTC, which is 0.3. Now you can see from the status code here, this one has a greater than sign, meaning it's best. Both of them are valid, so the star means valid, but this one is the best. So how does it determine which one is best? It is determined by checking the origin. Now here, the origin are represented by an I and a question mark. So let me explain. We have three origin attributes. The first one is called the I. Now, the I indicates that the network has been, please disable your video. So the I indicates that the route has been injected to BGP using the network command. So when you see I, that is what I means on the origin. Then you have E. E indicates that the BGP route has been learned through EBGP. EGP, Exterior Gateway Protocol. Of course, this is very rare because we no longer use EBGP, but it's still important because we can use a routing policy to change the origin attribute, as you're going to see here in the lab. So we can change the routing attribute to E, for example. Okay, then the last one is a question mark. Now, when you have a question mark, it simply stands for what we call incomplete. And it indicates that the BGP route has been learned through other methods. So learned through other methods, e.g. import command. So if a route has been learned through the import command, then you're going to have it with a question mark. Now, why are these three origin attributes important? What do they mean? Because each of them has a particular priority or preference, and this is how the preference is actually aligned. So a route learned via the I will be preferred, then E, then question mark. So that explains why this route has been selected as the best route, and not this other route which used the import command. You see, when we imported this route from RTC, we used the import command, so that's why we're having a question mark. When we imported from RTB to RTA, we used the network command, that's why we're having an I there. So that is how the origin attributes are actually used to select the best route. So I, network command generally, question mark, in summary, import command, when you use the import command. E is when the route has been injected in BGP from EGP. It is rare, but as I've said, we can configure routing policies. We can configure a routing policy to change the origin attribute to an E. And what that means is that that particular route will have a higher preference compared to one that has been learned through the import command, for example. So I hope you've understood about the origin attribute, a well-known mandatory attribute. Now let's look at the other well-known mandatory attribute called the AS path, Autonomous System Path. Okay, so let's look at this question here. So in the figure, RTA is in AS1 and can learn the route. It can learn this route on RTE, the 100.0.0, from either RTB or from RTC. So how does RTA select the optimal? How does it select the optimal route? And in that matter, using the AS path. So that's one of the problems that we need to understand. Number two, there are topology loops. So we can have a topology loop here. Let me use a circle. So we can have a topology loop here. We can have a loop here between those three routers. We can also have a loop here between these four routers. Therefore, routing loops may occur during BGP route transmission. So how does BGP prevent these loops? How does BGP prevent these loops? So let's begin by answering the first question. Okay, now when this route is advertised, either to this guy. Okay, let me first of all clear everything. Okay, so this route is advertised either to this guy, then it gets to this guy, like that. Now when that happens, the autonomous system numbers are recorded. The autonomous system numbers are recorded in this order. So this network began from AS4. So 4, then comma, then it goes to RTB, which is in AS2, like that. Then it reaches AS1, like that. So it came from 4 to 2 to 1. On the other hand, it can also be advertised. It can also be advertised like this. It comes to this guy, then to this guy, then it is advertised to this guy. So let's follow that path and see the ASs it's going to pass through. So if it follows that path, it's going to come from 4 and then go to 5, then go to AS3, then finally it will arrive on AS1. Sorry, on AS1 like that. So what happens is that the route that will be accepted by RTA is the route that has the shortest AS path attribute. So you can see this one is shorter than this one. So that is how RTA will select the optimal route, and the route with the shortest AS path. So in BGP, a router will select or prefer a route with a shorter AS path than the one with a longer one. Now, let's go to the second problem about loops. Let's go to the second problems now about loops. Now, as I've already explained, every time a route is advertised from one AS to another AS, the AS number is recorded in the AS path attribute. So that route is advertised to AS5, then advertised to AS3, then advertised to AS2. Now, if this guy tries to advertise the same route to AS4, AS4 will look at the AS path and see that, hey, my AS number is in this route, and therefore it will simply discard. It will simply discard that particular route because its AS number already has been recorded in that particular routing information, as we've seen when I was demonstrating the earlier example. Okay, so that is how the AS path is used to select the optimal route and to also prevent BGP loops. Okay, so let's see the next one. The next hop. So here we have two autonomous systems, AS100, AS200, and we have the four routers, RTA, RTB, RTC, and RTD. So we want to understand what the next hop is. The next hop is not very different from what we looked at when we were looking at IGPs like OSPF. But how they're treated in BGP is a little bit different from how they were treated in OSPF, for example. So when RTA advertises the network, so you can see that RTA has a network. This network is connected to RTA 100.0.0.0/24. So when it advertises it to RTB, what is the next hop? IP address. What is the next hop? Similarly, when RTB receives that network, it will advertise it through EBGP to RTC. Now, when that happens, again, what is the next hop? When RTC receives it, it's also going to advertise it to RTB through IBGP. Now, this time, the third scenario here has been explained through RTA. So RTA can also learn from RTB the network 200 that has been advertised by RTC. So the network 200 is this one here that is connected to RTD. My mouse is misbehaving. So this network here, 200.0.0.0/24. Now, when this route is advertised to RTC, RTC is going to advertise it to RTB, then RTB is going to advertise it to RTA through EBGP. So when that route is in RTA, what is going to be the next hop? What is going to be the next hop? So that is what we exactly want to establish here. Okay, so let's begin with the first scenario. Now, when RTA advertises this network to RTB, the next hop will be the outbound interface on RTA that has formed the neighbor relationship, IBGP neighbor relationship with RTB. So the next hop is going to be this particular interface, the IP address of this interface. Now, if the neighbor relationship had been established using a loopback interface, then the IP address of that loopback interface is the one that is going to be used as the next hop. So that answers the first scenario, that the next hop is going to be the outbound interface that has been used to establish the IBGP peer relationship. Whether it's a physical interface or loopback interface, that address is going to be the next hop. Now, what happens when RTB advertises this route to RTC? What will be the next hop? What will be the next hop? Now, when this happens, when EBGP neighbors exchange routes, then the next hop is placed as the interface that has established the EBGP relationship, the EBGP peer relationship with the EBGP neighbor. So that will be the next hop for that particular instance, for this particular scenario here. Now, the last one, the last scenario here, when RTA lands, when RTA lands from RTB, the network segment 200 that has been advertised by RTC. Now, let me clear. When you learn a route from an EBGP neighbor, and you advertise it to an IBGP neighbor, the next hop does not change. The next hop remains the same. So when this route here is advertised to a S100 by RTC, when it advertises it to RTB, then the next hop is this interface. And when RTB advertises it to RTA, the next hop remains as this interface. So it does not change to this interface. You see, for example, in OSPF, the next hop, if this was to advertise a route to this one, the next hop would have changed to this interface here. But in BGP, that does not happen. So when you are advertising an EBGP route to IBGP, the next hop remains unchanged. And this is also important in preventing loops. Because if the next hop changes, then RTA can also advertise it to another router here, for example. Then it will change its next hop to this guy. Then this guy can also advertise it back, change the next hop. Hi, my internet today. Am I the only one experiencing these challenges?
Will your service provider be Safaricom or you're using
Yeah,
bundle?
there's Safaricom. I'm using Safaricom actually.
Oh,
Hmm?
then maybe they have an issue on their end.
I'm sorry. Nilikuwa nimefika wapi? Hii point ya tatu mmeielewa? Yeah? Have you understood the last point I've just explained? That when we advertise an EBGP route to IBGP neighbors, the next hop does not change. And that also helps in preventing loops. So later on, you can read more about the next hop attributes in the notes. So let's go to the local preference. Let's go to the local preference. I don't know whether this is still available. Okay, yeah, it's still available. Okay, so before we look at the local preference, let's remind ourselves. So in the previous one, we just looked at the next hop. So next hop, AS path, origin are well mandatory, well known, mandatory. So right now, we want to look at local preference. Local preference. It is a well-known discretionary. So these three that we've just looked at, origin, AS path, and next hop must be carried in BGP update messages. All routers must understand them. Now, with local preference, for example, you do not need to carry it in a BGP message. However, it can be selected as required. So what is the local preference used for? What is the local preference used for? Okay. Okay, so the local preference attribute is valid only between IBGP neighbors, and it is not advertised in other autonomous system. This attribute indicates the BGP preference of a router and determines the optimal route for traffic leaving an autonomous system. The optimal route for traffic leaving the autonomous system. So how is that? So let's look at an example. Let's look at this example. So we have AS100 and AS200. Now, RTA can access this network on RTD via two paths. So RTA can use this path, or it can use this path. So which one is the optimal path? So you can see that this path has a lower bandwidth compared to this path. So this path is the optimal path. So how can we configure our network so that packets coming from RTA that are destined to this network can always pass through RTC? How can we do that? We can do that by altering the value of the local preference. By altering the value of the local preference and making it a higher value using what we call IP prefix and a route policy. Now, generally, the default local preference, is 100. Now, if we want this traffic to pass through RTC, we configure the local preference. We configure the local preference to a higher value, e.g. 200. So with BGP, a larger local preference value indicates a higher preference. So the router will select the route with the largest local preference attribute value as the optimal route. How to configure this local preference? We use an IP prefix to identify the IP prefix to identify what we call interesting traffic. That is traffic that is destined to the network 200.0.0.0/24, like that. Then after that, we now configure a routing policy. To invoke this IP prefix. So generally, that is how it's done. So RTA, as you've seen here, it's only valid between IBGP neighbors, the local preference. So when RTC advertises the 200 network to RTA via IBGP, when it advertises, it will change the local preference value to 200. When this one advertises, the preference value will remain as the default 100. And therefore, RTA will choose RTC as the best next hop. And therefore, we'll always send traffic via RTC rather than RTB. So that is how the local preference is used to select the optimal path. Okay, so let's move on and look at another attribute, what we call the multi-exit discriminator. This is an example of an optional non-transitive, if I'm not wrong. So let's see. MED. Yeah. Optional non-transitive. So a BGP router can ignore the message carrying this attribute, does not advertise this message to the neighbors. So that is the optional non-transitive. MED, multi-exit discriminator. Now, it is transmitted only between two neighboring autonomous systems. An autonomous system that receives this attribute does not advertise it to any other autonomous system. It determines the optimal route for traffic entering an autonomous system. Normally, I see the MED as the opposite. It is almost the exact opposite of the local preference. While the local preference determines the optimal route for traffic leaving an autonomous system, the MED determines the optimal route for traffic entering an autonomous system. So really, how is that done? Okay, so let's look at this example. So here we have a network 100.0.0.0. This network is advertised in AS 100. And you see we have two paths. So we have that path, and we also have this path here. So we can also see that this path that is leading this interconnection between RTC and RTE is slower than this one. This one has a higher bandwidth. So what we want is to use the multi-exit discriminator so that any traffic that is destined for the 100 network should pass via RTD. Should pass via RTD. So how the traffic enters. So we don't want traffic in our network to come in through RTE. We want it to come in through RTD. So we can do that by altering the value of the MED, multi-exit discriminator. Okay, so a few things to note. Number one, MED attribute corresponds to the metric value in IGP. So it's like the cost, so that is number one. Then it's used to determine the optimal route for traffic entering the autonomous system. Then number three, a router will select the route with the smallest MED attribute value as the optimal route. Number four, and the last point to note about MED is that the default MED attribute value is 0. The default MED attribute value is 0. So MED attribute is simply the metric determining the optimal route for traffic entering the AS. Router selects the one with the smallest MED. The default is 0. So look what happens here. If we want traffic to pass through RTD, what we do is that in RTE, we go and configure a higher MED value so that this one will remain the default, which is 0. So here we configure a higher metric value, a higher MED value, for example, 100. Then we apply some routing prefix to identify the traffic, and also we also identify, we also apply some routing policy to apply that particular MED, so that when this network is being advertised, when it's advertised to RTB, it's going to have a higher MED value, and therefore all the time RTD will receive a packet destined to this guy. It is simply going to send it to the one with a lower MED value, multi-exit discriminator, like that. So generally, that is how MED is used to select the optimal route. The one with the smaller MED value is preferred. Now let's look at the community attribute. Let's see where the community is. The community attribute is an optional transitive. So it's not a must that it is identified by all the routers. Just a few can identify, but it can still be carried in BGP messages and advertised to neighbors, even though it's not identified. So the community attributes. So we look at the community attribute. So the community attribute has two functions. Number one, to limit the route advertisement range. So how far you can advertise a route. Number two, max routes, so that routes meeting the same conditions are handled in a unified manner. So in this example, we have AS10, AS11, we also have AS12 and AS13. Okay, now in AS10, we have a network 10.1.10.0/24, and we also have a network in AS11 10.1.11.0/24. Now, to uniquely identify this network, we can use the community attribute value 10-12, and this one, in order to uniquely identify this network, we can use 11 :12. Now, when this network is advertised to AS12 and also this network is advertised to AS12, what RTC wants is to aggregate or summarize, as we called it in OSPF, summarize these two networks so that it only advertises a single summarized route or aggregated route to RTD. So what RTC is going to do is to take those two networks and summarize it to 10.1.10.0/23. So this network address and mask can be able to accommodate that subnetwork and this subnetwork. So that is one of the things that we can try and do so that we can be able to differentiate these two networks. Again, to do this, you have to configure an IP prefix on RTC, and you also have to configure a community filter that will now be able to identify each of these community values. So in the lab, you are going to also be able to handle that and see how it is done. Now, after doing that, we can also say that, hey, this network that you've received from RTA or from AS10 or from AS11, we do not want you to advertise it further. We do not want you to advertise it further. So when we don't want you to advertise it further, when we are configuring the community attribute, we can use what we call the no export. We can use what we call the no export parameter to ensure that when you get this particular route, you're not going to give it, you're not going to advertise it to the next autonomous system. You're not going to advertise it. So we use the no export parameter. Now, generally, the community attribute is classified into, number one, what you call well-known, and number two, what we call the extended community. Well-known and extended community. Now, we have four well-known community attributes. The first one is known as the internet. The second one is known as the, what we've just looked at, no export. Then we have the third one, which is no advertise. Then the last one is known as the no export subconfig. So the internet is what is called the default attribute, default community attribute. That is, all the routes belong to the internet. So by default, all community attributes can be shared. They belong to the internet. This means that these routes can be advertised to all BGP, can be advertised to all BGP neighbors. Then number two, we have the no export. So this one cannot be advertised to other autonomous systems. So you cannot advertise this route to other autonomous systems. Then this one cannot be advertised to other BGP neighbors. So what that means includes even IBGP. So you cannot even advertise it within your autonomous system. So that is no advertise. Then this one is used for what we call BGP confederation. And it is beyond the scope of this course. It's a topic that has been covered extensively at HCIE level. Okay, so now let's look at the extended community attribute. The extended community attribute is a 4-byte. Is a 4-byte list in the format of AA :NN. Also known as the community number. Now, what does AA mean? AA indicates an AS number, while NN indicates the community identifier that is defined by the administrator, by the admin. Generally, this number can range from 0 to slightly below 4.3 billion because it's 4-byte, so raised to power 32, 2 raised to power 32. So generally, that is it about the community attribute. So now let's look at the next. Oh, so we are done with the BGP attributes. Now we look at the BGP route selection rules. The route selection rules. Now, this one we're just going to read together. After a BGP router advertises a route to neighbors, each neighbor selects the best route or the optimal route. If this route is the only route to the destination, then the neighbor selects it as the optimal. So it's the only route. So simply, you don't have a choice. You don't need to look into any other options. Now, if there are multiple routes to the same destination, the neighbor selects the route with the highest priority as the optimal route. So these are the priorities that we want to look at. Now, if there are multiple routes that are destined for the same destination and have the same priority, then the neighbor compares the BGP attributes of these routes to select the optimal route. So generally, our BGP router compares the following attributes in sequence to select the optimal route. So the first thing it will do is simply discard any routes that have unreachable next hops. Then the next thing it's going to look at is it will prefer the route with the largest preference value. Now, the preference value is a Huawei proprietary attribute. We're going to look at it just now, and is valid only on the device where it is configured. So after the preference value, the next thing it's going to prefer is the local preference. We've already looked at the local preference, determines how the traffic is going to leave the autonomous system. And we've seen that a larger value is preferred for the local preference. Then it should prefer the routes in descending order of priority. So manually aggregated is simply summarized. Manually aggregated, we are going to see that. Automatically aggregated routes, then routes imported using the network command, that is I, then routes imported using the import command, question mark, then route learned from peers. After that, it's going to check the shortest AS path. We already saw that. So if all these are matching, it goes to this shortest AS path. Then prefers the route with the origin attribute. So I, and then E, and then question mark. Then prefers the route with the smallest MED. So if you have several routes to the destination, several options to the destination, you can always use the MED. You can also prefer routes that you've learned from an EBGP neighbor compared to a route that you've learned from an IBGP neighbor. Then prefer the route with the smallest IGP metric within an autonomous system. So the route that has the lowest cost within an autonomous system, you prefer it. If all those match, we go to preferring the route with the shortest cluster list beyond this particular training. Then you can also prefer the route with the smallest originator ID. Originator ID, and we know the origin. Then you can also consider the router ID. So the router with the smallest router ID, you prefer that route. Or finally, you can prefer the route that has been learned from the neighbor that has the lowest IP address. So that is the BGP route selection rules. You are not expected to be able to understand and have all this in your mind right now, but as you go on, you're going to maybe be able to understand them better. So there are about, I think, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So with time, please make sure that you conceptualize those particular rules in their exact order. Now, one of the rules we saw here was on the preference value. This one here, rule number 2. So prefer the route with the largest preference value. And we've noted that the preference value attribute is a Huawei specific attribute. So it's not on other vendor devices. So let's see how is the preference value used for route selection. Now, preference value is almost like the local preference, only that where it's applied is quite different. So the preference value attribute is a Huawei proprietary, valid only on the device where it is configured. It corresponds to the weight, so that is cost, weight in BGP route selection rules. So a larger preference value indicates a higher priority. So AS200 here, AS200 here has a network 200.0.0.0/24. Now, the administrator in AS100 wants to access this network segment over the optimal route, this one that has a higher bandwidth. So he doesn't want to access it via this one because this one has a lower bandwidth. So wants these packets to be forwarded to RTC, then RTD, then to that network segment. So how can the administrator do this? How can the administrator do this? So the administrator can configure an IP prefix. So on RTA, by the way. So this will be done on RTA. On RTA. So on this device, on RTA, configure an IP prefix to match the route. To match the route 200.0.0/24. So that is the first thing the admin will do. Number two, he will also configure a route policy. A route policy to invoke. The purpose of the route policy is to implement the prefix. So this IP prefix. Then number three, the admin will have to set the preference value of the route to, for example, 100. And lastly, apply the route policy in what we call the import direction. So those are the steps that this guy is going to take in order to achieve this. So once this has been configured, then the route, this route that has been configured with a larger preference value, is going to be selected as the optimal path, and therefore these packets are going to pass through RTC to add this network 200.0.0/24. So as you can see, it's almost like the local preference, but while the local preference we were setting it at RTC, now this one, the preference value is actually configured at RTA. So RTA is going to check the IGP cost and use it. So it's going to see that this one has a lower cost compared to this one. And therefore, it's going to use this particular route to forward its packets once we've configured the preference value. Okay. So the next thing we are supposed to look at is route aggregation. Route aggregation mode on BGP route selection. Okay, so generally route aggregation is simply route summarization. So we have manually aggregated routes, and we also have automatically aggregated routes. So, for example, let me say, so we have users on this network and on this network that are interconnected to RTB and RTC. Now, when this network is advertised, when these networks are advertised to RTA in AS100, then how will RTB prefer? Just a moment. Okay, sorry. So here, so aggregation modes. So we have two aggregation modes. So we have manual aggregation mode and we have automatic aggregation mode. Now, generally, manually aggregated routes have a higher priority than automatically aggregated routes, automatically summarized routes. So generally here, in this particular scenario, RTB has been configured with both manual and automatic aggregation in order to summarize these two routes to a single route before advertising it to RTA. So which route is RTB going to advertise to RTA? Is it the manually or the automatically? So obviously, as we've said, RTB will advertise the route with the higher priority, which is the manually aggregated route. So how to confirm that? We can do in RTB display BGP routing table for this particular network 200.0.0.0. Then we can see that we have two available. We have two. Okay, sorry. I think my internet flapped again. Okay, so we want to know which is it the manually or the automatically aggregated route that is going to be advertised. So we do display BGP routing table. We can see that we have two available paths, but one is best and one has been selected. So BGP routing table entry information for this network, we can see that it's an aggregated route. You can see that it's an aggregated route. And so this is the manually aggregated route. Then we can see the summary automatic route is the automatically aggregated route. So we can see that the manually aggregated route has been advertised to the peer. And the peer that it has been advertised to is this guy here, 10.1.12.1. But for the summary automatic route, well, you can see that it has not advertised to any peer yet. So we are not advertising the automatically summarized route because it is the manually aggregated route that has a higher priority. So generally, that is what we are saying there. So routes learned from EBGP neighbors are preferred. You remember we talked about this when we were talking about the route selection rules. So let's see this particular scenario. So here we have AS200 that has a network segment 200.0.0/24. Now, this particular network is advertised. This particular network is advertised to RTA and also advertised to RTB using EBGP. Now, RTB also through IBGP, RTB advertises that network to RTA. So in RTA's entry, it has two entries for this network. Two entries, one from RTC, another one from RTB for that network. So how does RTA select the optimal route? Now, generally, the rule is that RTA prefers the route learned from the EBGP neighbor. So it will prefer this one and install it in the routing table. And this particular route that has been learned through the IBGP neighbor is not going to be installed into the routing table. So EBGP over IBGP. So EBGP, whatever route you learned through EBGP, if they are going to the same destination, and you learn another route from IBGP going to the same destination, the one that you've learned through EBGP is the one that has a higher preference. Okay, so impact of intra-AS IGP metric on BGP route selection. So the other thing we said when we were looking at the rules, let me see here. One of the rules here was that it prefers the route with the smallest IGP metric within an AS. So what we've just looked at was this one, prefers EBGP route to an IBGP route. So right now we want to look at this one, prefers the route with the smallest IGP metric. So how does it impact the route selection? Okay, so here, so adjusting the OSPF cost enables RTA to access the network segment 200 over the high bandwidth links. So let's look at this. So we have this network on RTD. RTA can access that network through that path or through this path. Obviously, this second path has higher bandwidth and therefore is the optimal route. So how does RTA use the intra within an AS IGP like OSPF cost to determine or to select the best path? So what happens here is that on this interface that is connecting RTA to RTB, we can configure the OSPF cost to a higher value, maybe 100. So we go to this interface and then we use the command OSPF cost 100. Now, once we do that, it will have a higher cost compared to this particular interface. And when we do that and we display the content of the IP routing table, we can see the entry for the 200 network. We'll now have the next hop of RTC. No. The next hop actually is the interface here on RTD because it was advertised through BGP, then IGP. So the next hop is not going to change. But generally, if you do a TRASAT, you can see that indeed these packets now are going to pass through RTC because this one has a higher IGP cost. So the one with a lower IGP cost is going to be preferred because this one is going to have a BGP cost of 1. You go 100 over 100. The reference bandwidth default is 100. So over 100, it's going to give us 1. But now this one, we've changed it to 100. So that's why the packets are going to pass through RTC. Okay. So let's go on and look at the router ID, which can also be used, and also the IP address. So the last rules here. The last rules here. So whoever has the smallest router ID or the lowest IP address. So if all the others have matched. Okay. So in AS200, we have the 200.0.0 network. It's going to be advertised through RTB and also through RTC to RTA. And if we do display BGP routing table, we can actually see that we have 2 entries to that network. We have 2 entries to that network. So this one that has a lower preference value, local preference, is the best so far. So how can we select the optimal path? The optimal path to accessing this network from RTA. So how, if everything else has matched so far, then the next thing that is going to be considered is, you see, we can use this one. We can come here, or we can use this one. So the first thing the router is going to check is the router IDs. So the one with a smaller router ID, in this case it's RTB, is going to be preferred. But now again, when using RTB, we can go to RTB either using that first link or using this link. So using 2.1 or using 1.2.0. So which one do we use? Again, when it comes to the interface, RTA is going to choose the interface, is going to prefer the interface with a smaller IP address. So this is the one that is going to be selected. So packets are going to pass through the 1.2.0, then to this guy, then to that particular network. So generally, that is how RTA is going to access the 200 network. So RTA accesses the 200.0.0/24 within AS200 through RTB. In particular, it uses the outbound interface 10.1.12.1. So it uses this particular interface as the outbound interface because it has a smaller IP address value. Okay, so that is how the router ID and the IP address impacts this particular thing. So an example for configuring a BGP routing policy. I want to give you this as a reading assignment before you do the labs. So before you do the labs, you can go through this scenario. It's not very difficult. So I want to leave it for you. If you'll have a question, you can let me know. Okay. So the next bit is on BGP route aggregation. As I said, aggregation is simply summarization. We want to summarize routes, and there are several benefits to summarizing routes. So BGP transmits routing information between autonomous systems. As the number of AS autonomous systems increase, or even the number of routers within an AS increase, then the BGP routing table becomes very large. So resulting in 2 problems. Number 1, storing the routing table will occupy huge memory resources. Then also, transmitting all these routes is going to consume a lot of bandwidth resources. So those are two problems actually, memory and bandwidth consumption. Then the last problem is frequently updating and withdrawing routes will affect network stability. So once we have so many routes, if there's any problem for a particular route, then the network will flap. We'll have updating and withdrawing. So the same problems that we explained when we were talking about OSPF summarization, route summarization. So it's the same reasons why we need to summarize routes, BGP routes. So BGP route aggregation is designed to solve two problems. So the following describes BGP route aggregation. So we're going to look at why is it necessary. I think we've already talked about that. Number two, route aggregation configuration. How do we configure? We talked of manual and automatic aggregation. Then we are also going to see another problem that is going to come up as a result of route aggregation, BGP route aggregation. Okay. So let's look at this scenario. So AS100 and 200 each have 4 user network segments. You can see we have four. And you can also realize that they are contiguous, meaning that 8.0, 9.0, 10.0, 11.0, and then this one 12.0, 13, 14, they're following each other, they're consecutive. So AS300 is connected to AS400. Now, this router on AS400, this router RTD is a low-end router. So RTD has low processing capabilities. So it is required that RTD can access the network segments in AS100. So it can be able to access these networks and these networks, but do not need to receive the specific routes. So how do we meet this requirement? So as we said, advantages of route aggregation, number one, to save on memory and bandwidth, and also processing. Number two, to reduce frequent flapping of specific routes, which will make the network unstable. So let's see, how do we do this? How do we configure this? Okay. So we want to look at BGP route aggregation, and we are looking at static routes. So how do we aggregate static routes? Okay, so AS100 has 4 network segments. So RTA in AS100 shields specific routes using route aggregation and advertises only the aggregated route. So the summarized route 10.1.8.0/22 to RTB in AS200. So it's only going to advertise the summarized route. So how do we do that configuration? You go to BGP 100, you establish the neighbor relationship with RTB on the directly connected interface, and you also specify the AS number where RTB belongs. Then you use the network command. You use the network command to advertise the aggregated route, the summarized route. So network, then 10.1.8.0, then the mask 255.255.252.0. So the 252 is /22. Then after that, you configure a static route. You configure a static route. So IP static route, saying when you want to come to this network, that has this mask, then this is the next hop, null 0, null 0. So anytime you configure a static route to aggregate specific routes, you must specify the next hop to point to null 0. This is because the aggregated route is not identified by a specific address. So hello? Hello, can I be heard?
Yes.
Okay,
Yes, I can hear you.
poleni sana. I really don't know what is happening to my internet today. Okay, so other than static routes, we also have what we call the automatic. We can also configure automatic aggregation of routes. So again here, RTA is connected to 4 subnetworks. When advertising that to RTB, we want to advertise a single summarized route, a single summarized route. Reason being, this guy here is a low-end router, so we don't want to overwhelm him with a lot of routes. So to do that, we go to RTA, we create BGP 100, we do the peering with RTB, then we use the command summary automatic. So once we use the command summary automatic, we can create a routing prefix. We can create an IP prefix to identify the individual networks. So IP prefix to identify the individual networks. And then after that, we create a routing policy to invoke the prefix R1. So we simply create that. And now in the BGP configuration, we do import routes direct route policy R1, so that these are the only networks that we are aggregating using the summary automatic. So the router is automatically going to find the network address and the appropriate length, prefix length, or the mask that can be used to summarize these 4 routes. So that is how we do automatic summarization, by configuring the command summary automatic. Then lastly, we have manual aggregation. So again, the scenario is just the same. We don't want this guy receiving a lot of routes. We want to summarize this. So how to do that? With manual aggregation, we use the command aggregate. Now generally, just this is enough. Aggregate, then the network address and the mask that will be able to summarize these 4 into a single address. Now we can go ahead and add the command detail suppressed. So what is the purpose? What is the purpose of suppressed? Detail suppressed. I'm trying to remember. Mhm. Okay. Mm. Mhm. Wow, I'm unable to remember, but I think I'm going to mention this. If I don't mention it before we end, I'm going to talk about it when I research about it. It has really escaped my mind. Okay, so after doing that, you can use the network command. You see, even though we've actually, I think I've remembered the details suppressed and what it means. Even though we've aggregated the route into this, we're still going ahead to advertise using the network command and also using the import route command. But now when we say details suppressed, it's going to suppress all these advertisements that we've done on any of the networks that will match that IP prefix. So for any of these networks, they are simply going to be advertised using this manually summarized route. So they're going to suppress these individual advertisements. So that is what the details suppressed, I think, if I can recall, really stands for. Okay. So routing problems brought about by BGP route aggregation. One of them is loops. One of the problems is loops because when we aggregate routes, let's look at this scenario. So number one, AS300 aggregates its routes into, so these two routes are aggregated into this. So number two, AS200 aggregates the specific routes from AS100 and AS300 into this. So these routes that have been received, 1, 2, 3, they are aggregated into 10.1.0.0/16. Now, when AS200 advertises the aggregated route to AS400, so when the aggregated route 10.1.0.0 is advertised to AS400, this route does not carry the AS path attributes for the specific routes. So you see, when we advertise this route, we carried the AS path. Hey, I'm coming from 300. Hey, I'm coming from 100. But when these two are aggregated, to 1 to 10.1.0.0/16, then we lost the AS path, and now the AS path is just 200. And therefore, at number 3 here, when AS400 forwards the received aggregated route to AS300, AS300 checks the AS path attribute of this route and does not find its local AS number. So it accepts this route. As a result, a loop may occur. So you see, this route came from AS300. It was aggregated, sent to 400, and it's now back here. And because when we lost the AS path information when the routes were aggregated at AS200, so this guy is simply going to accept it. He's going to accept it. Why? Because it will check the AS path. It only has 200 and 400. So mine is not there, so I'm going to accept this route. But this route is part of what came here. And therefore, with that, a loop occurs. So how do we handle this scenario? How do we handle this scenario? Now, to handle it, two AS path attributes. I don't know, did I talk about AS path? Did I talk about AS path attributes? Attributes. Okay, AS path attributes, two. So one of them is called the atomic aggregate. Atomic aggregate, which is a well-known discretionary attribute. And the next one is known as the aggregator, which is an optional transitive attribute. So the atomic aggregate attribute is used to inform inform other routers that information has been lost on downstream routers. So really, this particular an update message that carries the atomic aggregate attribute informs its neighbors that the path information has been lost. So this one, used to inform neighbors that path information, only AS path, by the way, so that AS path information has been lost. So that's the purpose of the atomic aggregate. Then the aggregator, this one contains the AS number and the router ID of the router that initiates route aggregation. It carries the AS number and the router ID of the router that initiates the aggregation. So for example here, the aggregation is initiated at AS 200. So the aggregator attribute is going to carry that information, the router ID and the AS number of that particular router. So let's look at this one. What happens here? So AS 300 aggregates its specific routes into that, then forwards. You see we have 300. This one does not aggregate, just sends the two networks. The AS path will have the value 100. So when AS 200 aggregates the specific routes from AS 100 and 300 to 10.1.0.0/16 and sets the AS path attribute of this route to carry path information of the specific routes. So how does it do that? You can see here. So when advertising this, the networks that have been aggregated from the different ASs, their path are actually recorded in brackets. So 100, 300. Then, of course, now it's coming from 200. So on step number 3 here, AS 400 forwards the received aggregated route to AS 300. AS 300 checks the path attribute. So it's going to check the path attribute and it's going to find its own AS number, 300. So it will simply discard the route and therefore prevent a loop from occurring. So that is how the loop is prevented from occurring. Now, the AS path attribute has two types. The first one is called the AS sequence. The AS sequence, so that you can understand how that 100 and 300 are carried. And the second one is called AS set. Now, this one records sequenced ASs that packets pass through. Now, AS set records unsequenced ASs that packets pass through. So what does that mean? So here we are carrying 300 and 100 in AS sequence. Here 200 has been carried in AS sequence. Here 200 and 400 have been carried in AS sequence. But now, after aggregating the two routes from two different ASs, we store these two, not in any sequence, they're unsequenced. We store these two in the AS set attribute. And therefore, if this network is advertised back to AS300, it's going to look at the AS set and find its number there. And therefore, it's going to discard that route, thereby preventing a loop from occurring. Okay, so I can see someone has oi, leo mimi nimepotea. Pole sana. When you do the labs and maybe go through the theory again, you're going to understand them. But most of these things are not very easy. They are quite cumbersome to comprehend and understand at the very first time. And it's also a very long topic, as I had mentioned earlier, but fortunately, we've come to an end eventually. Poleni sana for the long and tiring lecture. I can only imagine how it feels from your end. Okay, so a volunteer to help us with the first question and another one to help us with the next question. Are you there? Winnie, Gadudi.
Oh, yes, I'm here.
Okay, you can pick one.
I'll do the first question. Which of the following attributes are BGP well-known mandatory attributes?
Yes.
Of origin, the AS path is a mandatory attribute, and the next hop is a mandatory attribute. The local preference is a well-known discretionary attribute.
Okay. And it takes time to understand those things. So give yourself time.
Yes.
Okay, thank you very much, Winnie. Macau? BGP uses TCP port number.
Which of the following port number? 179. 179.
Exactly. So it uses port 179. What uses port 21? TCP port 21? 20 and 21.
OSPF.
20 and 21.
OSPF.
I think it's FTP.
FTP.
Ama?
I don't know.
I'm not very sure. I think it's FTP, 20 and 21.
It's FTP. It's 20 and 21 is FTP.
Yeah, it's actually FTP. Okay. Thank you, guys. Thank you for your time. That's the end of this chapter. Asanteni sana.